So this is a vector, and by the end of this video, you are not just going to memorize its textbook definition, you are going to feel exactly what it's doing in space. But to get there, we first have to uncover a massive lie that most mathematics textbooks tell you right from page 1. A misunderstanding that completely breaks your intuition the moment you try to build a 3D game engine, train a neural network, or simulate real physics. Our understanding of this arrow didn't begin in a classroom. It began on the water over 2,300 years ago. Greek mariners sailing the Mediterranean faced a constant invisible problem. When a ship was trying to cross a channel, it was never dealing with just one force. The wind blew the hull of the ship in one direction, while the deep marine current swept the keel of the ship in another. Two distinct forces, two completely different directions, yet the ship didn't split in half, and it didn't travel down both paths, one after another. It moved along a single, unified path. In the ancient texts attributed to Aristotle's school, thinkers documented a profound geometric truth. If an object is moved by two simultaneous forces, its true path tracks the exact diagonal of a parallelogram built from those two forces. Aristotle could see the geometry clearly. He could draw it in the sand, but he couldn't write it down as an algebraic formula because the symbolic mathematics required to calculate it didn't exist yet. It was a physical observation frozen in geometry. It took over 2 millennia for that drawing to turn into modern math. Sir Isaac Newton used these directed lines in 1687 to compute gravity, but he lacked the dedicated notation for them. In 1843, the Irish mathematician William Rowan Hamilton spent a decade trying to invent a system to calculate these 3D rotations, creating an incredibly complex system called quaternions. It wasn't until the 1880s that an American physicist named Josiah Willard Gibbs stripped away Hamilton's hypercomplex layers, isolated the simple directed arrow, and gave us a clean vector language we use till today. Most people's modern introduction to vectors look exactly like this. A teacher draws an arrow on a graph and delivers the standard definition. A vector is a mathematical quantity that possesses both a magnitude, which is simply a fancy word for its physical length, and a direction. On paper, this definition is entirely correct, but it sets a dangerous trap for your intuition. It leaves you with a structural mental model that a vector is a static physical object, a literal line segment glued directly onto a specific piece of graph paper. If you view a vector as a fixed object trapped at a specific coordinate, the math becomes incredibly confusing the moment you enter dynamic environments, because in the real world, vectors are applied in a range of these environments. These include and are not limited to marine technology, space technology, complex physics simulations, as well as computer games.
Hey, don't kill me. Elijah. Elijah, come now. Elijah, come. Elijah, I call you.
Let's strip away the grid entirely and look at two completely independent locations in space, point A and point B. They are just static positions. A vector is not point A. It is not point B, and it isn't a static distance between them. A vector is the literal instruction required to displace you from point A to point B. Think of it as an active command. Translate through space exactly this far, pointing in precisely this direction. A vector is not an object. A vector is a move. And here is the exact breakthrough that a German mathematician, Hermann Grassmann, realized in 1844. which fundamentally changed physics. An instruction does not care where it starts. Look closely at these three arrows. They live in completely different areas of the screen, but because they possess the exact same length and point in the exact parallel direction, they are not three different vectors. They are the exact same vector repeated 3 times. Because the vector is the move, its identity is completely independent of its location. Whether you apply this instruction at the origin of a universe or at the farthest edge of a galaxy, the instruction stays identical. The move doesn't change. Now we face a structural challenge. How do we write this spatial movement down? How do we convert an abstract arrow floating in 3-dimensional space into pure calculable numbers that a computer can compute? We do it by breaking the single diagonal move down into 3 independent perpendicular steps, one along each primary axis of our space. Instead of trying to track a complex angled path in a single chunk, we quantify it step by step. How far does this instruction move along the x-axis? Positive 3 units. How far along the y-axis? Positive 2 units. And how far along the vertical z-axis? Positive 5 units. These 3 numbers are what we call the components of the vector. They are literally an ordered set of sub-instructions. Move 3 units east, 2 units north, and 5 units up. Combined, they execute the complete unbroken shortcut. As our perspective shifts around the coordinate space, notice how these 3 independent paths trace out the structural framework of a solid 3D box. The vector itself is the absolute internal diagonal of that box, and calculating the true length of this shortcut isn't a new mathematical formula. It's simply the classic Pythagorean theorem we all know, but this time extended into 3 dimensions. We take the x component squared plus the y component squared plus the z component squared and take the square root of the entire sum. The result, the square root of 38, is the absolute magnitude of our vector, the exact physical distance of the move. To ensure this mental model never breaks when you see a vector in the wild, let's anchor it to 2 real-world concepts. First, look at a vector as a pure route template. If a navigation app tells you to walk 3 blocks east, turn left and walk 2 blocks north, and take an elevator up 5 floors, it is giving you the long route. The vector is the absolute physical shortcut through the air. The components are the constraints of the grid. The vector is the real direct displacement. The second vital anchor is velocity. Imagine a spacecraft coasting through the vacuum of space. It doesn't have a grid beneath it, but it possesses 2 undeniable properties. It is traveling at a specific speed, and it is heading towards a specific point in the cosmos. That is a velocity vector. The length of the arrow represents how fast the ship is moving, and the orientation of the arrow dictates its path. Inside a modern game engine, this is exactly how motion is calculated. The engine doesn't store a list of where the ship should go. It simply stores these 3 raw numbers. Every single frame, the engine reads the velocity vector and adds those exact changes to the ship's position. If you want to change the trajectory, you don't rewrite the ship, you simply alter the vector components. Now that we've traced history and built the geometric intuition, let's step completely out of the animations and look at this live inside our 3D lab environment. Here is our vector, living inside a real rendered environment at a flat static angle. It looks like a standard 2-dimensional textbook drawing, but the moment we rotate our perspective, the geometry comes alive. You can see the true spatial depth. It isn't an object glued to a background, it is a direction vector slicing through space. Notice exactly what just happened. I shifted the starting point of the vector across the grid. The position changed completely, but the direction and total length remained totally untouched. It is the exact same instruction, simply applied at a different spot in the universe. Two distinct arrows floating in different areas of space, but representing the exact same mathematical instruction. This interactive playground is going to serve as our sandbox for this entire series. We are going to use this exact space to visualize dot products, cross products, and complex linear transformations. In our next video, we are going to take two separate vectors and add them together. And because you now understand that a vector is an active instruction of movement rather than a static line, vector addition isn't going to feel like a tedious algebraic formula. It's going to feel like absolute common sense. Thank you for staying with me in this video. Don't forget to like and subscribe. I'll see you in the next one.